developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
The philosophy of what we do at HySonic focuses on wave control. The company has been involved in external flow control, so controlling waves that naturally occur on the external shell of a hypersonic vehicle. And these waves are typically in the range of 100,000 to a megahertz, so very high frequency waves. But we've also been applying the same philosophy, same tools, same skill set to internal flow control, specifically in the propulsion system of hypersonic vehicles. The AFRL Regional Hub is interested in advancing the TRL level of our technology as it pertains to external flow control.
During the first increment at HySonic Technologies, we were able to develop and improve an ultrasonic bench test capability that allows us to characterize the acoustic absorption capabilities of potential aeroshell materials. Hypersonic missiles suffer from an acoustic phenomenon that causes early laminar to turbulent transition. By using a HySonic Technologies aeroshell material, we can delay that transition and improve its flight performance. In my hand, you see one of the samples that we're going to be using for the next increment here. These porous samples allow us to validate our bench tests in order to characterize these materials. The next step will be for us to place these samples in a thermal environment so that we can understand how that thermal aeroshell environment is being impacted while flying at high Mach numbers.
I'm happy to report two major breakthroughs that the HySonic team made in the last few months. One was towards the end of the first increment, where we have designed purely computationally and with some heuristic knowledge, a new form of control that out of excitement was immediately tested at the Air Force Research Labs, and its effectiveness was confirmed by experimental data. This breakthrough number one can be attributed to the first increment of our effort. We also had breakthrough number two, and that was a recent award by the DOE for a very prestigious supercomputing allocation that will allow us to further strengthen and increase the fidelity of the computations that led to breakthrough number one.
So we've obtained some really interesting new results from our recent aircraft carrier test article and test campaign in the Air Force Research Laboratory. We're able to actually compare two different measurement techniques that are commonly utilized for mapping out locations of boundary layer transition, one being surface pressure transducers, which give us the unsteady surface pressure content at the surface, which we can then integrate to look at the overall RMS of that surface pressure fluctuations. Okay, so if we do this along a ray from left to right on our model, we can see in the blue and red lines here in this graph that these lines start to abruptly increase at some point, and that abrupt increase is commonly defined or used as our definition or indication of the boundary layer entering a transitional state. That unsteadiness starts to amplify in an extreme way. Okay, but what's interesting about this particular test article is it also allows us to identify boundary layer transition via another common metric, which is infrared thermography, specifically surface heat flux. That yellow line along the same axial location along the model indicates an abrupt increase in heat flux much farther downstream than the PCB surface pressure sensors, which opens up a totally new, interesting avenue for exploring the underlying physics of this particular mechanism of boundary layer transition that we and our Air Force colleagues are extremely excited to explore in more detail. The other thing that we're working extremely hard on during the second increment and going into the third increment are some really interesting redesigns of this aircraft carrier. Given its large size, it being the largest model ever tested in this particular facility, we've actually found some interesting and somewhat alarming high values of stresses and strains within the model, which we can see some here in this image, that we're looking to address in order to ensure the safety and large safety factors that the Air Force Research Laboratory requires. Once these are done, then we will continue to use this in order to test our future material flow control techniques.
In my hand here, we have a low porosity sample. We use stainless steel samples that have cylindrical pores in them with a known depth and diameter used to calibrate and refine our ultrasonic absorption bench test. This low porosity sample has fewer holes than the high porosity sample, but it has the same nominal diameter, depth, and pore diameter. If we take a look at the experimental plot here, you can see the experimental data is given by a red dot that has an error bar. This error bar is calculated by taking this test over and over again and finding out how repeatable these results are. 2 times the standard deviation to be particular. Now we see that we have a lower theoretical bound and an upper theoretical bound. Rott's theory is a theory in fluid mechanics that is based on the Navier-Stokes equations and applied to this kind of acoustic environment. The lower bound simply represents the nominal pore depth of this sample with a minus tolerance, and then the upper bound represents the nominal pore depth of the sample with a positive tolerance. And what you see is that the difference between the depths for these 2 curves is very little, 0.06 millimeters, which shows that our experimental data is falling right in between the nominal depth within plus or minus a certain tolerance. In my hand here we have the high porosity sample, and similar to the low porosity sample, it contains pores that have a certain diameter and depth. The only difference is that it has more pores, allowing there to be a greater surface porosity. Very similarly, if we take a look on the experimental data is given by a blue dot that has an error bar, also representing the repeatability of these results. The lower curve and the upper curve also represent a certain tolerance above and below the nominal pore depth. And what that implies is that based on the pore depth of the sample operating at this frequency, you're going to get different absorption results, which means that we can tune these depths for certain acoustic frequencies that we wish to target. And that kind of knowledge will help influence how we will design flight grade materials that have more arbitrary geometries, but can have an effective nominal pore depth involved.